Good afternoon. Sorry I couldn't be here earlier, joining in for the start of the proceedings and the lunch, but unfortunately had lectures this morning on office hours and couldn't attend. So what I'm going to be talking about is the electric vehicle research we're doing here with my colleagues, Professor, if I may, Professor Bhattacharya and Professor Kasarani, which he already made a presentation in some of the work we're doing in smart chargers. We've been working on these for several years now. I'll give you a bit of an overview of the presentation. I'll describe who the sponsors are, motivation for our research, the objectives. We've looked at the studies at the generation transmission system level, and the distribution system level is probably of more interest to you, on smart chargers. Or the companies who have supported this work, companies, institutions are here on the screen. There are quite a few. A good part of this work is being pursued with Hydro One. Okay, so that's a life of its own. What are the motivations? Well, motivations are basically, well, there's an issue of, in the transportation sector, it's an issue of energy demand, and it's an issue of greenhouse gas emissions, right? So I'm not going to go through this in a lot of detail. I guess there's an issue of supply of oil and the need to support or green this particular area, right? As we all are all aware of. There's an issue from the point of view. On the other hand, you have the electrical system. Hypersensitive. Maybe I need my own computer here. Anyway, the infrastructure issue in terms of the grid is basically subutilized, right? Basically, it's designed to supply peak load, and you rarely use it for that, right? You are talking about what a few percentage of the time in terms of the maximum utilization of this. So there's an opportunity to merge these two systems, right? Transportation and the electrical system, particularly at night. And there's another motivation behind it, particularly in Ontario, which is basically the greening of our generation supply, right? So we're basically getting rid of as much as possible of greenhouse gas emissions. So as you can see from this plot from the ISO, from the OPA, pardon me, how according to the plan of how the generation is changing, the generation mix is changing. Eventually, we're going to significantly reduce. And we're pretty close to that. Significantly reduced. We're already seeing that in terms of coal, right? The gas emissions. So the idea is, well, can we merge these two? In which forms? How can we do that? And at what levels? And what would be the issues associated with that, right? And there's a great motivation in North America for that, not only Ontario, but particularly green systems. Quebec is looking at these, BC is looking at this, and Ontario is certainly very interested in that. So the idea is to look at the issues that these bring about, particularly from the power system point of view, at the generation, transmission, and distribution system level, and then with that, basically determine approaches, analysis, impact, etc. That's basically what is behind this. So these are the objectives. Okay? We're trying to investigate the technical and economic feasibility to improve the utilization of the Ontario grid to supply basically transportation or energy for transportation. Now, considering basically what the state of the Ontario infrastructure is. Okay, so we're trying to be as realistic as possible. So we started with generation and transmission system studies. Say, well, what happens at that level if we have all these loads added? Because they can be significant. I guess we're talking about in an PHEV 30 kilometers. We're talking about, depending on the size of the vehicle, you're talking about from 4 kilowatt hours, 4 or 5 kilowatt hours to 8, 9 kilowatt hours, right? So if depending on the level, level 2 or level 1, you're talking about loads on the order of 4 kilowatts or loads on the order of 1 kilowatt, right? Depending on the level of charging. And if you consider that in a typical residential house in Ontario, we're talking about 6 to 7 kilowatt peak load. In some cases, you could double the load of of the house, right? Depending on the type of level charging level, and depending also on the size of the vehicle. But however, basically the idea was to look at those issues and see what kind of impact that has in the grid. Okay? So we developed basically an optimization approach an optimal planning approach to try to tackle these issues. Okay? So we developed a model, which is basically briefly described here, and did some studies. So basically, this is what we looked at. This is basically what you can obtain from this. So if you look at the utilization of the grid for charging only at night of certain type of vehicles, PHE30, a reasonable mix of different type of vehicles, not a lot of load, level 1 charging, okay? Basically, this is what you can accomplish at night from a back of the envelope calculation. Basically, if you look at this, you could utilize the grid 100%, and you can almost charge 100%. If all the vehicles in Ontario were PHEV30, you could charge all of them. Now, this is a silly approach, right? This is a back of the envelope calculation, which is, by the way, this is what has motivated politicians to say, oh, well, we can certainly do this, right? If there's underutilization, why don't we go on? I mean, we can use the fill in the valley approach, and we can basically transform all vehicles to electrical. Well, it's not as simple as that. Okay? In reality, you have to look at the available generation, whether it's available generation at night. You cannot just utilize the system 100% of the time. And this, we came with this optimal approach and said, well, how can you obtain, based on the transmission constraints, generation constraints at night, how much of the vehicles can you charge? And that will depend on the year. The planning year, because it depends on the capacity of the system. Basically, you can go as low as, we were looking here at 2008, as low as a few percentage, to as high in some years, depending on the available generation, to 30, close to 35%, which is significant, but as you can see, is far away from the 100% approach, which basically people have argued. The other problem with all of these is that these will have an impact on pricing. Now, that's not necessarily bad. This is the profile of pricing in July 2008. You start observing already negative pricing, which has become more prevalent, with more generation, less load, more prevalent at night. And it certainly makes sense, for example, if the prices, because this will have an impact on price, this will improve the pricing profile. So it has certain advantages. All of this considers that you will never charge these loads in the middle of the day. Given the size and the problems already we have with peak load, that's not a good approach. Okay? Now, we looked at the distribution system. At the distribution system, we looked at different cases and say, well, let's do a study on distribution system. We concentrated on a typical benchmark system, and we also looked at a Hydro 1 feeder, okay? With laterals, with unbalanced conditions, et cetera, et cetera. We're talking about, at the few kilovolt level. We did not look at the low voltage level, which is another issue that we did not address ourselves. But it's certainly a problem in all of this, because that's probably where the bottleneck is in many of these studies. So we generated a model with some constraints. It's basically an optimization model. And the intention of this model was, well, can we coordinate the charging of these vehicles and see how many of them we can charge? And basically, the intention is you look at a feeder, it has certain load profile and balance, using the TOU, approaching the problem with different forms, minimize energy, for example. At 90% penetration, meaning 90% of the houses had vehicles, basically. This is basically what you observe. Basically, is that the load, basically what happens is the system is utilized, for example, in this example, one of the feeders reaches its limits basically at night. So most of the vehicles are being charged at night. This is assuming that you can coordinate the charging of the vehicles. Uncoordinated charging, basically what would happen is that the peak will have peaks exceeding the feeder capacity, because more people would charge it as soon as they get home. All of them connected, and then you have problems with your feeders. Okay? So uncoordinated charging is simply not an option. Now, the question was, how do you motivate the users to do that? And that's a very good question. How do you get the users to buy into this, not just go and connect? I guess there are many approaches have been suggested. One is pricing. Another approach is basically, well, especially for level 2 charging, you cannot just go and put your level 2 charger there, right? You're going to need permission from from different levels, and that would basically, that's when the LDC will have to get involved, right? At some level, some approvals are going to be required, and at that point, basically, one can use policy approaches to address this problem. These are other examples of different approaches where depending on the approach and how you coordinate this vehicle, what you're trying to accomplish with this coordinated control, basically what happens is the curve can flatten up instead of having peaks, right? And these are different values, basically comparing the different approaches. Now, one of the conclusions of all this work, and with this I finish, one of the conclusions of all this work is for this to be successful, especially when you have this problem of clustering, right? For this to be successful, for be viable, the only approach, the only meter approach, the only way to do this is either you redesign the system to supply these big loads, which is basically a no-no, it's impossible, right? Or you approach the system with smart charges, which we all have talked about that, right? In which coordinated charging is going to have to take place. In other words, you cannot just plug your vehicle and charge it as you wish. There's going to have to be some control over that charge. That opens the door to many possibilities from the point of view of, well, allowing basically these vehicles to charge properly first, then optimally utilize the network in terms of coordinating, for example, the charging and the charging of these vehicles with the availability of wind and solar, for example. All of those issues come to the fore, and with a smart charger, basically make this feasible, and it's an intelligent part of a smart grid approach, right? Intelligent way of doing this. Now, as it was well said, how do you get people to buy into this? And I guess that's going to be has to be a policy issue, pricing issue, something that has to it's not only a technical problem, right? It goes beyond that, and that has to be discussed with the authorities, with the LDCs have to be involved, et cetera, et cetera. So with that, I'll stop. That's basically an overview of the work we're doing here. And we're basically developing these smart charges, the work we're doing with Professor Canizares. In other words, how we are able to communicate with these devices, how the devices can coordinate with each other, how these devices, which is what the work that Professor Canizares was really explaining, how these devices communicate or consider the impact on the grid to charge or not the grid, charge or not the vehicle. Also, we are considering vehicle-to-grid technology, even though so far that's not feasible. Right? But looking at the future, who knows? We might be able to use that energy for other purposes. Okay, thank you, Tracy.
Any questions for Claudio?
More a suggestion, or I'm not sure how you're developing some of the smart chargers. Some of the smart meters that we have, there is the ability to put communication protocol within them. Not for a large amount of data, but communication protocol. And some of the ideas is along the way to enable home area networks.
Yes.
One of the thoughts might be to flip that the other way around, is to look at that communication port as a way of saying, what chargers can you allow on the system at some given point in time? And I don't know how it would work. I haven't figured out how it would work, but certainly it would probably be somewhere in the same vein that communication would work for outage management systems or something like that, where this thing says, I'm down this much, I need this much charge. You know, when can I go on kind of thing, and looking at the number that are already connected to that feeder, then you may say, okay, I'll switch you on or not through an algorithm back at the utility. I don't know if that's
you raise an interesting point. That's basically the way that we were seeing the problem. There are several issues with this. First, the meters. We have done a lot of work with meters. Actually, we're deploying equipment in houses, in Milton and in feeders in Hydro One. With another project we have about energy management systems. What we have basically encountered in all of this is that the smart meter is not that smart. That the communication system or pipeline, the AMI, is basically designed for basically billing purposes, not real-time control purposes, not data acquisition. So eventually what we had to do is basically give up on the smart meter, even though we developed Zigbee communication protocols for a computer, energy computer, to communicate with the meter. at the end of the day,
Yeah, the aim line is not.
we had to basically get over that, get into the internet, and then get into real-time, basically control and approach. That's one of the problems I would like to mention, right?
Yeah.
For this to work, you're going to need basically real-time access to the smart meter, minute by minute type of stuff, right?
Well, and that's good for us to know, because one of the issues we have in going to the regulators and say to them, we need to spend money on this. And that happened with the smart grid and the smart meters. And the issue of putting a higher level of communication technology into the AMI, many utilities were turned down because the OEB said to us,
yeah.
You don't need that.
Exactly.
But having research like this that says, if you're going to handle this, here's what you need for communication systems, that helps us with our regulator.
And certainly, yeah.
We need to invest money in this.
Correct, and what our discovery with Milton Hydro was, because we're also looking at other levels of control, not only the vehicle, but other stuff in the house or in communication with the house. And in that process, we basically discovered this, that no, the smart meter is not a good way to go about it. And we realized that was some policy decision at some point.
Yeah.
But now you're stuck with, billions of dollars investment on this, at least hundreds of millions of dollars in this system. So anyway, that's life. So what we've done is bypass it, go through the internet, but the approach we're taking is exactly the one you described, which is, okay, the utility in a feeder has basically a computer intelligence, has an algorithm. We have developed an algorithm, and the algorithm is going to tell, well, you charge, now you charge, now you charge, for this amount of time, right? In a way, we're still developing those algorithms in a way that work real time, right? That you can actually do it in real time, in an optimal way. Now, what you define as optimal is a bit of an issue. Optimal for whom, right? For the customer, reduce the cost, for the utility to avoid peaks, or what? So that's an issue that needs to be addressed. But basically, the approach is the one you described. So basically, a centralized feeder control in which you tell, for that feeder, you communicate with these vehicles, in our case via internet, and we tell them, look, now you charge for so much time, according to the constraints of the feeder, the customer constraints, because comfort is very important. You cannot ignore the customer constraints. You cannot go as a utility, all-knowing utility, and tell them that you charge this way, right? So it needs to be coordinated with that. And that's part of the work we've done, for example, the energy management system, which is basically these energy hub management systems basically consider the customer preference. And there's actually a firewall between the customer and the LDC. So you have communications between them, but also only to control certain amount of flow of information. For in the case of the smart charges, you're going to need more access to that, right?
So you're going to need an internet address.
Basically, and you're going to have to decide when or agree on when to charge and not. Okay.
Okay, thank you, Dr.
All right, thank you.
All right.
Thanks.
We